Okay, so it's if you haven't already seen it when you came in, this radio is here, and you'll notice that there are two dials on the front. One is for tuning, and the other is for the regeneration or the feedback coupler that will allow you to change the amount of coupling to the tuning circuit, and regeneration takes place. And this knob down here is both an on-off switch as well as a volume control, which will explain how that works. And the two jacks in front are for plugging in a pair of headphones, probably of around 2,000 ohms impedance, in order to give enough resistance for the load to be generated across that output. So let's go to the next slide now. And that is a diagram that's on the inside cover of this radio, so that Jack provided a pictorial of what the controls are. And now the next slide. And the back of the set. So the battery terminals, because it runs on a battery, the 45 volts battery is for the B plus, or the vacuum tube supply, and a 6 volt DC supply for operating the filaments. On the other side, there's a ground and an antenna connection. And we'll explain how all of this works together. So we'll go to the next slide. Okay. Now, first of all, I'm going to give you sort of a very brief overview of the radio. We'll come back to this and explain it in more detail. This seems to be as good a representation, I believe, as to what the radio actually looks like in terms of its wiring diagram, but I can't guarantee 100% that everything will be exactly as Jack did it here. And so you'll see right away that it has a single tube, a 01A type, that operates it. You'll see the tuning circuit here, which is this front control for tuning in a radio station. You'll see the tickler plug-in circuit here with a capacitor that allows you to adjust the amount of feedback into the circuit, positive feedback, that will cause this regenerative effect to take place. So that explains those controls. You have an antenna hooked up, of course, to this control here and to this input tuning circuit. You see here the filament supply that operates off of a 6 volt supply coming in through the on switch right in the front, and a volume control. Now the volume control just adjusts the amount of battery voltage that gets to the filament. A 01A operates on 5 volts at 0.25 amps, in other words at 250 mils. So there should be a dropping resistor in here so that you don't crank up the volume control too far and overreach the voltage for the filament to be in danger of maybe burning out. That should be in there, but it's underneath a platform right here, so I can't vouch that it's there. You'll see at the top there's also a radio frequency coil, or a choke, somewhere in this range, likely 2 to 5 millihenries, and then that feeds your output here with the jacks, allowing you to put in a 2 kilo ohm phone to listen to the thing. Okay, now, and at the bottom here I've listed the plug-in coils and what their ranges are. But we'll have pictures of that, so let's go back to the pictures and we'll show where all these things lay in the radio itself. Okay, so we're looking inside, and there's the 01A tube, and over here is the tunable capacitor for the tune circuit and the dial for the radio reception, radio stations. Over here is the regenerative feedback capacitor and the adjustment knob in the front. And then you look at some of these other parts and pieces. You'll see you have a set of coils here. So here's one that's plugged in.
Excuse me.
And that coil has 2 windings on it. One for the tunable radio station coil, and the other for the tickler coil, or the feedback coil, that causes the regeneration effect to take place. We'll get more into that in detail. You notice that it comes out here, and the output of, actually it's the output of the tube that also, it parallels the coil. There's an RF choke here. That's actually another coil operating as a choke to restrict certain radio frequency signals from getting through to the output. And here you'll see the grid leak circuit going into the grid of the 01A. And this actually is not a fuse, it's a resistor, an old-time resistor of 5 megohms. And there's a capacitor underneath it, a mica capacitor that's in parallel with it, right here. That's 150 picofarads. And together, conjoined, they represent the action in a grid leak detection circuit for the tube to work and detect the actual modulation signals coming through from a radio frequency carrier. And over here, this little platform allows you 4 other coils, plug-in coils. They're sitting there just in storage, but when you use all of these coils, it allows you to tune this radio in 5 bands from about 600 kilohertz right up to 30 megahertz. So that's interesting. That's an unusual kind of regenerative radio. You don't see necessarily that usually happening. Now, with that, let's go to the next slide. Now I'm focusing in here on the grid leak circuit. You notice all the right-angled wiring, and that's typical too of the age in which these radios came out, which was in the 1920s. So this is a replica of a 1920s radio. And there's the resistor, the 5 megohm resistor. You can even read it there. And up here, you can see the capacitor. You can even read that. It's 150 picofarads. It's stated in microfarads, but it's equivalent to 150 picofarads. That going to the grid circuit. Okay, next slide. That's just a picture of the coils. You notice that each coil has 2 sections. It's got the tuning coil section here that parallels with a tuning condenser, tuning capacitor for tuning in the radio stations. And it's got this tickler coil here, which is used to pump energy into the circuit to feed back positively and cause the regenerative effect to take place. We'll get into that. And here are all the other coils. Now you notice that they're listed in terms of the meters or the wavelengths that the coils are cut for, 45 meters to 95 meters. This, you can see one here is 200 to something up there, 25 to 55 meters. So they're all calibrated in terms of meters rather than frequencies. But according to the frequency formula for changing into wavelength, you can easily do the exchange and find out what frequencies these cover if you want to go by frequency rather than wavelengths. Okay, next slide, please. So this is just a final picture of the inside again. The layout you can see. Now, why I chose this picture is because not only does it show you the whole layout inside, but you get a picture of the 01A tube. Now that's interesting because if you look at the base, it's a Bakelite type base. All right. Let's spend just a little more time on explaining what's happening. Now, first of all, you might wonder, for a sensitive radio, why did they only use 1 tube? Well, the reason for that was that tubes in the beginning were very expensive and hard to obtain. And so you didn't want to try and design a radio circuit that would have 6 or more tubes in it. You tried to make do with as few tubes as you possibly could, and yet still receive a readable signal. And so the 01A was a tube that started to come out in 1920, and you'll notice that it has a directly heated cathode, which is the filament, and as the filament heats up, electrons are given off. And I assume that everybody knows that electrons are just the negatively charged subatomic particles that orbit around the nuclei of atoms. Then they have to pass through a grid. And the grid influences the amount of current that can go through to the plate up here, which is running at plus 45 volts. The grid then carries a signal in here and allows for amplification to take place. Now, the amplification factor of these tubes was only about 8. So by more modern standards, where you had amplification factors of 100 for triodes and even up to 500 or more for a pentode, that's pretty low gain to work with. So what could have been done? What was done actually then is once you have the radio broadcast station tuning mechanism here with the coil and the tuning capacitor. In Jack's radio, it's 140 picofarads. And the grid leak detector, you can then capture a radio signal from a broadcast station. It will be passed through the tube, both the modulation of the signal as well as the current from the plate or into the plate, and then it will progress up through here to the tickler coil. The tickler coil is in phase with the coil here, and it will feed back energy by reason of inductive coupling and sort of pump the circuit here into greater and greater capability of gain, more so even than the 8 restricted degrees of gain that you get in the tube itself. And we'll talk a little bit about how that's done. That's a bit of a miracle in effect. You notice the antenna comes in and connects to the grid circuit, of course, because you want to get the incoming signal from the radio station to be directed into the grid for amplification. Now in Jack's radio, he's got a little bit of a variation of the signal that, of the feedback signal that's associated with the tickler plug-in coil. In a lot of the regenerative radios, they had a physically rotatable coil that was nestled into the main tuning coil, and by rotating the coil, you could vary the amount of inductive coupling from the coil, the tickler coil, into the main tuning coil, and thereby control the amount of gain or regeneration. Because in dealing with positive feedback signals or feedback energy into the coil, you're dealing with the benefit of regeneration, which greatly increases the amount of signal that can be carried through and along with the plate current at radio frequencies right through the circuit. So what Jack did, instead of doing that more physically challenging type of development or build, he put in a throttle cap here. Now it is also a 140 picofarad tunable capacitor that is in parallel with this coil. So in effect it becomes another tuned circuit like this one, but instead one designed to feed back energy and to generating more out of this guy. And so by doing that, he changes the amount of positive feedback going through this circuit into this, rather than using a physically rotatable coil as a tickler coil to generate the amount of feedback. Of course, the idea being that with regeneration, if you push it too far, it breaks into oscillation, and this whole circuit becomes an oscillator rather than a very sensitive receiver. You go from here into the radio frequency coil, which is a block on the RF or the radio frequency stuff coming here, and only allows the lower frequency audio to come through. And then you've got a load expressed here with the 2 kilo ohm phones picking up the signal, and you can actually hear something. Is that on the screen? Yeah, okay. So once again, down here you have all the plug-in coils. Notice that the formula for figuring it out yourself, if you want, is that frequency in hertz is equal to volts, velocity of the wave, which is basically the speed of light, because radio waves travel at the speed of light, and meters per second over that of lambda, which is the wavelength in meters. One wavelength is this, from a positive going signal front to a negative swing and back to zero again. That's lambda, or one wavelength. And the number of times it does that in a second is called the frequency. Typically, and then at broadcast AM frequencies, you'll go from about 540 kilohertz right up to about 1.6 megahertz. So then with the plug-in coils, he picks up not only the broadcast range, and here's the first one here. This one covers half of the broadcast range up to a megahertz. This next coil covers the rest of it, 1.5 meg, well, it's almost at the end, up to 3.53 megs. And then he's picking up the short wave bands with the rest of this stuff here, all the way up to 30 megahertz. Okay, now, the miracle of resonance and radio. allow me a bit of a review here, first of all. So, resonance is a physical phenomenon in which basically you can get a whole lot of energy out of something that you pump with a very small amount of energy. In other words, it represents a huge amount of gain expressed in a particular vibration or frequency. And the basic circuit that was discovered was the LC or LCR circuit here, sometimes called a tank circuit. And with the use of an inductor, which is basically a coil, and a capacitor, which is basically just two plates separated by an insulator, you could generate significant amounts of energy with the phenomenon of resonance. And it's a miracle, in a way. It's a miracle. Think of it as a tank, and it's sometimes called a tank circuit. So this circuit here is like a water tank, a reservoir with water in it. And you can pump water into it. And in fact, in order to fill up the tank, you've got to pump water into it. And if there's leakage, then the pump can continue to circulate the water and keep it at a certain level. So this circuit, because it stores electrical energy, and it stores it in a particular way that it allows it to retain that energy, and not only retain it, but build it up. And there lies the miracle. Now, it's impossible in the short time frame we have now to get into all the niceties of how an inductor and a capacitor work together. But basically, they store energy in opposite phases, and they build in an oscillatory fashion one against the other. So it pumps back and forth, just like the pump that keeps the reservoir filled. And the result is that you not only store energy, but you get a whole lot more for the price of a whole little put in. I'll explain that in a minute. Notice also, though, that there's an R, there's a resistance. It's an effective resistance in the circuit. Even if you have a single coil and a single capacitor and you don't put a resistor in, you have an effective resistance because it represents the dissipative losses, mainly from the coil. The Q factor is basically the reactance of the coil and the capacitor over that of the resistance, the effective resistance in the circuit. And when you look at that Q factor, it can be 100 over that of a circuit that is not operating. That is just the plain tank circuit. So you're talking about a gain of 100 because of the Q of this particular circuit, just with a nudge of energy into it. So how does that happen? Look, if you turn on some power to the circuit, give it a spurt from a battery or something like that, it'll go into an oscillation. How does it choose that oscillation? Well, the value of L and C are cut to a certain frequency. They have a resonant frequency that they want to oscillate at. And if you give it a little spurt of power, it will start to resonate and then quickly die out. So you would think that, gosh, in order for these to be pumped, you'd have to have some energy of the same frequency that would allow you to generate that kind of a resonance. What happens, in fact, is that with the transient of power going in from a battery to the circuit, there is bound to be a particular frequency associated with that resonant frequency for the tank circuit, if you follow that. And that will cause it to oscillate, because the transient, of course, contains a whole lot of different frequencies. And we can get into spectral analysis and so on, but we don't need to do that. Just accept that takes place. Now, what's interesting is take this circuit and just let it sit there, but now expose it to a radio signal. Here's a very tiny little radio signal coming in there. You see the whole number of cycles? It's maybe just a particular carrier over time. And so what happens is, if the tank circuit experiences it, it will start from a very small oscillation and build up to the highest amount it can build up. And then when you cut off that signal, it starts to degenerate, it decays. Now, notice that this signal is so much bigger than the little one here. And as I said, there's a Q of 100, which means there's a gain of 100 in the size of that signal without any amplification, just with that circuit. What happens? Well, these little pulses associated with the radio signal build up, and they build one on top of the other, almost like the compound interest on a bank account, accumulating. And so the energy accumulates and keeps on building up until it reaches a maximum. Why doesn't it go farther? Well, because of the dissipative losses associated with the effective resistance of the circuit. It can only go so far, and finally you're losing more energy than what you can pump the circuit up to give, and therefore you reach a maximum. Okay, so all of that was understood and known by the end of the 19th century, went into the 20th century. And Fleming brought out his valve, his vacuum tube diode valve, in 1903. And Lee DeForest brought out his triode tube in 1906. And it introduced a grid along with a plate and a cathode that could fluctuate the amount of current going through the tube. He called it an audion, but despite the similarity to audio signals, it was basically just a triode, a 3-element tube. Now, so after that, once you had the electronic apparatus available, the tubes, in order to detect and amplify, Edmund Armstrong came along in 1912, and he designed and built the first oscillator. And the idea of the oscillator is that you take a tank circuit or an LC circuit, just like the one we've been talking about here, and you want to stimulate it into producing a signal. So if you just generate a little bit of electricity in there, it'll quickly die out, right? But fortunately now we have a vacuum tube that can amplify that little signal. It can feed through a tickler coil, and it can generate, by reason of mutual inductive conductance, and strengthen the signal here and produce an even much larger signal. Another way of thinking about this in connection with the effective resistance is that this is working on a negative resistance principle. Now, if you look for a negative resistor as a passive device, you'll never find one. Negative resistance only works in conjunction with active components, with active electronics. That is, with electronics that emit electrons. Devices like semiconductors and tubes. The famous tetrode tube, a 4-element tube that came out later in the last part of the 1920s and early 30s, by reason of its action, produced a negative resistance curve for part of its operation. Gun diodes today do the same. You know, the diodes that are used in radar guns for measuring your speed on the highway. Other devices as well have that negative resistance factor. So negative resistance is this. Now here is an IV plot. Current, which is I, is expressed on one side of this graph, and voltage, increasing voltage, goes the other way, expressed here. With an ordinary resistor, if you increase the voltage and current across the resistor, it would represent a straight line. That line is called linear. And that corresponds to Ohm's law, where resistance is equal to voltage over current. Here's negative resistance, and it takes a downward track, and this means that as you increase voltage, you get decreasing current. That's a negative resistance factor. Now, wouldn't it be nice if you could take that negative resistance factor and then allow it to overcome the effective resistances and dissipation associated with this tank circuit? Well, that's exactly what this circuit does. It's sort of like adding on another pump to the tank circuit storage and allowing it then to not have to run dry. So think of it now as a tank, as a storage tank with water in it, and you have a pump. But the pump, unfortunately, is not 100% effective. It leaks, so there's always some that's being, you're losing some of the basic flow. But now what if you have another pump that picks up the loss or the leakage from that pump and then recirculates it into the tank? Well, that's exactly what's happening with the circuit. And so you come out And with the tickler coil then, you can, and with the benefit of negative resistance as expressed in this whole circuit, you can then pump this thing up, keep it going, and express not only the amplification from the original signal of the tank circuit, but a great much more besides that. And if you're wondering how much that gain could now be expressed at, well, originally it was around 1700, but with increasing efficiencies in the design of these things, they got it up to over 15,000. So it means a little signal could be amplified 15,000 times to give you an appreciable output, and that was pretty important with very weak radio signals being received. In a way, I've kind of explained a little bit about the amplification capability of a circuit like this, the regenerative radio. What I haven't touched on too much is the grid leak detection. So let me just take you up to this slide, and here you have a radio frequency carrier. This is the kind of radio frequency that you would see, or pardon me, radio wave that you would see coming out from a transmitting station without any modulation. And so you express modulation onto that radio carrier, and it looks like this. And the curvature of the undulations here represent the signal, which is usually audio or music or something like that. So it consecutively suppresses and then enhances the size of the radio frequency carrier wave. Now, if you just receive this, why wouldn't you hear anything? Yeah, so if you take away the RF stuff here, the positive and negative swings of the modulation signal would simply cancel each other. No good. What you need to do is rectify it. So it cuts out all of the bottom, say the bottom portion of this wave, and leaves only this top. Then you've got the modulation envelope isolated by itself without any cancellation effect, and that's called the process of detection. All detection, all radio detection depends upon rectifying this signal into a uniform or one-directional signal flow in a diode type of detection or some other form of detection. And so the grid leak detection system, which this radio uses, a regenerative radio uses, is a form of diode detection. Now you look at this thing and say, well, where's the diode? I don't see any diode there. I've produced here what is called a transfer curve, and on one side again we have current expressed in microamps, very small, and on the other side down here we have a graph that shows voltage, grid voltage, and this has to do with the grid. This is the grid transfer curve. Now for a minute, just don't bother with this portion and don't bother with this portion. Instead, look at this nonlinear line here. And this represents the current versus voltage operating line in a diode and also in the grid circuit. Now how does it happen? Well, it happens because as electrons are emitted by the filament here in the 01A tube, a small number of them are captured by the grid, and depending on the bias on the grid, it allows a certain amount of grid flow or grid current flow to take place. And so there's a certain very tiny current, less than a microamp, that is flowing out of the tube this way. And the interesting thing is that originally they only had a capacitor there, and then the first people who were using the regenerative radio were playing it, and then they found out that they would lose their detection. And they said, what's happening here? This is strange. But what was happening is that this capacitor would charge up, and as it increased its charge, it would start to act as a block to the signal. So one guy came along and he touched his finger on the grid, and the detection signal came back. And he said, okay, so obviously you have to leak the grid current away. And a resistor was put in here as that leakage path to allow the grid leak to really work properly. Okay, so where's the diode effect? Well, okay, you've got the operation here, and it turns out that this curve is nonlinear, it tends to straighten out and become more linear as it should increase up there. And ordinarily you would get most of the sort of the power distribution of a diode expressed that way. But what's happening here is you come down and toward these very small amounts of grid current and grid voltage, there's a nonlinear effect associated with their emission. And the grid leak detection is put here, an operating grid potential is put here, and you'll notice that it's on a nonlinear portion of the curve. And if you take a signal voltage coming into the grid, this one here, and express it across this operating point over here and extend it in terms of what's happening with the rectified grid current, you'll notice that the current waveform is lopsided. And there's more positive going here than there is negative going here. And the amount of rectified grid current then is represented by that traced line here. So in effect it's like a diode, but not a full diode, but there's enough of a rectified grid current associated with that that carries forward across the tube along with the radio frequency current in the tube, so that it can be detected on the other side after considerable amplification. That Armstrong had produced this circuit, originally a takeoff from his original oscillator circuit in 1912, and the regenerative radio then came to look like this. It used a grid leak detection system, and it allowed then positive energy to be fed back from the tickler coil into the main tuning coil, causing great amounts of amplification to take place in an effect of a negative resistance capability associated with the tube and the tank circuit. How much? So I mentioned, I think, the gains originally were around 1700, but they were increased finally, optimally, to 15,800 was the greatest that was obtained, as far as I could find out. What does it represent? Well, that's a gain of 10, let's just take a gain of 10,000, which is not even as much as that. And you express the gain as voltage in, voltage out versus voltage in. A radio signal will come into your antenna if it's a strong station at about 100 microvolts. And if you have a gain of 10,000, which this circuit is capable of doing, you're going to have a 1 volt signal coming out. And that's enough to give you some signal into the phones here, and you're able to hear your voice and your music that way. And of course, if you can increase the gain even more, you'll have more of a signal coming out. But what about very weak stations? You know, you could get down to just a few microvolts of signal. And that is something where super regeneration takes place and takes effect and has a further benefit. But it looks like I've run out of time, and I don't want to keep everybody here past the point. I'll have to take that up another time. Just as a final review of what's happening here, you have the tank circuit that is generating an oscillation, and this gets amplified in the regenerative circuit. And then if you look at the waveform that comes out, you have the sound or the signal waveform being carried by the radio frequency carrier. And both get amplified. But then later on, you have an RF filter here which extracts the radio frequency stuff and allows the audio stuff to get on through. So there, in a very short time, is an explanation of the regenerative radio.